Welcome, everyone, and thank you for joining us for today's sessions in the AI/EI webinar series on understanding potential revisions to the PG Asphalt Binder Specifications. This is session number 2 of a 3-part webinar series focusing on proposed revisions to the binder fatigue parameter for the NCHRP 09-59. Part 2 today builds on Part 1 by focusing on how asphalt binder specifications can better address fatigue cracking. Again, our speaker today is Mike Anderson from the Asphalt Institute, that is a member of the AI/EI team. Before we begin, I would like to go over a few housekeeping items. So please keep your microphone muted during the webinar. If you have any questions, please post them in the chat box, which you can access by clicking chat in the meeting controls. I will be compiling the questions during Mike's talk, and the presenter will address them at the end of the webinar as time allows. Any unanswered questions due to time constraints will be responded by separately. And this webinar is being recorded, and a link to the recording will be provided later. All webinars are posted on the AI/EI website as well as on the AI/EI YouTube channel. If you are not aware of it yet, the first webinar, the Part 1 webinar, has already been posted on the AI/EI YouTube channel, and I just posted the link in the chat box. Moving on, to the next slide. This is basically the second in a 3-part series. Today we're covering Part 2, and then in about a couple weeks, on December 4, we're gonna basically have our last part of the webinar series, which will focus on the expected impacts of these recommendations from the research, and including in how many changes may affect lab operation, testing procedures, and the PG binder specifications. On this slide, you can obviously find the link to register for the next webinar. You can also visit our AI/EI website in order to get access to the webinar registration link. Before we get going, I'm gonna go through some of the disclaimers. So this material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange only, under the cooperative agreement number listed on this slide. The U.S. government assumes no liability for the use of the information presented. Except for any statutes or regulations cited, the content of this presentation do not have the force of law and are not meant to bind the public. This presentation is intended solely to provide information on existing legal requirements and agency policies. The U.S. government does not endorse any products or manufacturers, and any references to AASHTO or AASHTO M standards in this presentation refer to private voluntary standards. Compliance with them is not required under federal law. With that in mind, let us get started, and I'll now turn it over to Mike to kick off the presentation. Mike, the floor is yours.
Okay, thanks, Ellie. As Ellie mentioned, this is the second part of a 3-part series, and part 1 I'll kind of recap here in a minute, but let me start by thanking really the folks that make this possible to be able to speak with you today. And there's a number of people that were responsible for the research. So first, I guess, thanks to the project team members of 959, specifically what we're talking about today, but also the other teams for projects 960 and 961. Those are all binder related projects that have recently either been completed or are being completed by NCHRP, and the lot of good information there. There was also an implementation project by NCHRP called 20-44 Prin 19, which is a little awkward to say. It's easier to see it in writing. But that one was all about looking at these research projects and trying to help users understand what they mean. And that's kind of the basis behind what we're doing today. Thanks, of course, to this cooperative agreement for supporting this effort and being able to share with you all what some of the potential changes look like. And last but certainly not least, from my standpoint, thanks to our member companies of the Asphalt Institute who really support what I do and give me the opportunity to do things like this. So if you haven't watched part one yet, I'm going to give you the Cliff Notes version of this. If you want to go back and watch it, you can. But what did we talk about in part one? We asked the question, what is fatigue cracking in asphalt mixtures? What affects fatigue cracking? How do the material properties of an asphalt binder affect fatigue cracking? And how does the PG Asphalt Binder Specification address the contribution of the asphalt binder properties to fatigue cracking? So wanted to take it all the way through the process of understanding we've got a specification. It says it's addressing fatigue, specifically the binder's contribution to fatigue, but how does all that work? So let me address those questions for you kind of in order. Apologize. So when we talk about fatigue cracking, what do we mean? It's repeated loading from traffic that results in longitudinal or alligator cracking. That's what most often we see. It's when tensile strain at the bottom of an asphalt layer exceeds the strength of the mixture and the cracking propagates to the surface. That's what we call classical bottom-up fatigue cracking. We also see something called top-down cracking, which is really caused by excessively age-hardened asphalt. So it's not traditional fatigue in the sense of, it's strain on the asphalt layer that propagates up, but it's more age hardening. So mostly when we talk about fatigue cracking, we're talking about the classical bottom up fatigue cracking. As far as what affects it, asphalt mixture stiffness is a big contributor to that, which is a function of really a lot of different things, but the in-place air voids, the volume of the asphalt binder that's in the mix, the asphalt binder stiffness itself, and how that age hardens. Applied loading or stress also matters, and the strain that is applied into the asphalt layer, and that comes from the asphalt layer thickness. The thicker the pavement, the lower the strain is going to be at the bottom of the layer, and that helps reduce the number, or it helps extend the number of cycles to when a fatigue crack is going to occur. As far as how do the material properties of an asphalt binder affect fatigue cracking, if you're looking at the asphalt binder itself, it's the stiffer asphalt binder that's after aging. That can lead to an increase in cracking in thinner asphalt pavements or where you have higher strain conditions. And last but not least, how does the current PG Asphalt Binder Specification address the contribution of the asphalt binder properties to fatigue? And that comes from, I'm going to close this poll. That comes from limiting the stiffness of the asphalt binder through the use of the dissipated energy parameter. That parameter is G star times sine delta. It's determined after aging, and we're simulating longer term aging with the PAV, and we're doing it at intermediate temperatures because we're trying to simulate more of what the temperature of the pavement looks like year round. And that needs to be a temperature that's appropriate for the climate and for the asphalt binder grade that you're using. The spec limit that we use currently was based in large part on laboratory testing as well as a field experiment that was called the Zacco-Wigmore Asphalt Test Road and recovered binder properties that came from that test road after 8 years in service. Excuse me. So the learning objectives for this session, why do we need a new intermediate temperature binder parameter in M320 and M332? How did the 959 research team address the research objectives, specifically relating asphalt binder properties to asphalt mixture fatigue? What are the research recommendations for improving the PG Asphalt Binder specification? We'll touch on all that in this presentation. Excuse me. So why do we need a new intermediate temperature binder parameter? If you go to the problem statement from NCHRP 959, it makes a statement that you see on the screen that many pavement engineers and researchers believe that the current superpave asphalt binder specifications do not adequately predict the contribution of binder properties to mixture fatigue performance. They know that the current PG specification, as we mentioned, it was largely based on the Zaka-Wigmore test road, which came about in the 50s and 60s. We know that the materials used then, the traffic loadings that we had at that time are different than what they are today. But what they saw on that test road was that there was a dramatic increase in fatigue cracking when the estimated loss modulus of the binder exceeded a value of about 3 megapascals, which is 3,000 kilopascals. This was from part one. We showed this slide, which came from the Sharp A367 report. And on the left-hand side, that's the figure that came from that report of the Zaka-Wigmore asphalt test road. And it shows recovered penetration on the y-axis versus percent cracking. And there's a dashed vertical line. I'm going to see if I can highlight it here. This dashed vertical line that you see here, that it represents 10% fatigue. So that's the 10% fatigue cracking, and they called that the failure criterion. And what they looked for was where this curve crossed that point, and it was right about a penetration value of about 30 decimillimeters. And that was after 97 months in service, or about 8 years. They converted that over, as you see in this is figure 222 from Sharp Report A367. They converted that over into G star and G star sine delta, and then got these vertical lines here, and of course the cracking line there, to come up with the 3 megapascal or 3,000 kilopascal limit. Later on, that limit was changed so that it was then changed to 5,000 as the specification was being developed. So, and I just mentioned that actually in the second bullet point that you see there, it was, the limit was raised from 3,000 to 5,000 just to reflect some of the variability they saw in the data, and also looking at current binders and how they graded within the current system that they were looking at. They did do lab fatigue testing of asphalt mixtures during Sharp that generally confirmed the relationship with G star sine delta. Another slide that we showed in part one, this was what they called their 8x2 experiment. They used 8 asphalt binders. They used 2 different aggregates, 2 air voids, 2 strain levels. And they did all that, and they analyzed what happens to fatigue life as you change these various properties. And what you can see, the y-axis here is cracking resistance. So as mixed fatigue life increases, the cracking resistance increases. This is the binder stiffness, G star times sine delta after thin film oven aging, so short-term aging, at 20 degrees C and 10 hertz. This was the test temperature and frequency of the mixed fatigue testing. So binder fatigue or binder stiffness at the same temperature and frequency as what we had for the mixed fatigue test. And what you see is a rational response for many of these graphs. This is just one of them with one particular aggregate, one particular air voids. And what we see is that generally speaking, mixed fatigue life decreases or cracking resistance decreases as binder stiffness increases. And we see that across the board. This is the 700 microstrain or the high strain mix testing. This is 400 microstrain, which is the lower one. And you can see the same response in each one of these. The other thing that you see out of this graph in particular is that strain is very important, because in this case, we can say this binder has a low stiffness and it's got a pretty good fatigue life, relatively speaking. As you get to the highest stiffness values, we get very low fatigue life. But if you lower the strain level, you can get even the hardest of the binders perform very similarly to the best of them, if you will, just by changing the strain level. So it's more than just the binder properties that are going to matter, and that was kind of the focus of what we talked about in part one. There's lots of things that play a role in what's going on. But for a PG specification, we're focused on what the binder contribution is. So we want to talk about that just a little bit. So there have been several researchers that have noted shortcomings with the parameter, specifically that G star time sine delta does not seem to correlate well to fatigue performance in the field. If you go to a paper in 1997 by John Deacon, John Harvey, Akhtar Tayabali, and Carl Monosmith, they talk about the influence of binder loss modulus, which is G star times sine delta, on fatigue performance. And what they noted was that the loss modulus or the loss stiffness of the binder is not a sufficient indicator by itself of the fatigue performance of asphalt concrete in actual pavement structures. If you go to some follow-up work, not for that work necessarily, but work that was done in the later 90s and early 2000s, there's NCHRP report 459, which was from the NCHRP 9-10 project. And they talked about the lack of correlation between mixed fatigue and binder fatigue at intermediate temperatures, and the need for something else that talked a little bit better about fatigue resistance. In this case, they were looking specifically at modified asphalts, but still we're seeing some questions about how that worked. This is just an excerpt from NCHRP report 459. There are 4 graphs on the left-hand side, and more interested in you just looking at the lines there and how they are in the data points and actually seeing what the numbers are or what the R-squared values are. I can tell you the R-squares are pretty low in general. But these were for 2 different types of aggregates, 2 different types of gradations. So it was limestone and gravel, coarse and fine, with these 9 different modified binders or binders that were used within that study. And just what the response looked like in terms of mixture fatigue versus binder fatigue. And you can see correlations not particularly good in this particular study. If we highlight just the top left graph, you can see it a little bit better. Where in this case, we've got data points that are really scattered. So this is, they go anywhere from 6,000 kilopascals to about, in this case, 10,000 kilopascals or 10 megapascals. And you've got about the same fatigue life for those materials. So the best that you can say is that there's a trend line that does say that fatigue life gets better as you have softer materials, but that's a really, really weak response. And it's, for the most part, if you took that trend line out, you'd be hard pressed to figure out where to draw that line necessarily. So it was just an example that we know that the G star time sign delta is not relating directly to what we're seeing, at least in laboratory fatigue life. So maybe we need to look at something a little bit different, perhaps something a little better. That was all the premise of the 9-59 research, what their findings, and this is an overview of those findings. The next presentation that we're going to have is going to talk about the impacts of what those findings are and what they're going to mean. So in this case, the project objectives here that you can see, which is basically looking for an asphalt binder property that's a significant indicator of fatigue performance, not the sole tie to fatigue, but as an indicator of that, and identifying practical implementable tests, one or more tests, if you will, to measure those properties that can be put into a specification. So it was a practical approach here that they wanted to find something that would work within the specification, but not be difficult to implement, not require lots of new equipment or tests that were perhaps new or unproven. It was just, what can we do that's going to relate to that? If you want to read more about it, it's NCHRP report 982, and you can read a little bit more detail about what they did in this study. Don Christensen was the principal investigator. Nam Tran with NCAT was a co-PI. So their key findings. One of the things that they noted, or one of the key things they noted, was that applied binder strain is a more of a function of traffic and pavement thickness than asphalt binder or mixture properties. That's a caveat at the beginning. It basically says that what's going to cause the strain in the pavement or the failure strain is going to be thickness, it's going to be traffic. Those are going to have a huge impact. But as I said, we're focusing on what's the binder's contribution. So even though they start off by saying binder's not as important as some other factors, because we're using it in a specification, we have to address that. So how do you do that? Well, you reduce the strain in the mix and in the binder through fatigue life, and then eventually you're going to evaluate how those binder properties are going to relate to fatigue. So it depends on a lot of factors, but what you can address within a specification are applied binder strain, binder failure strain, and fatigue exponent. We'll talk a little bit about those. So fatigue life increases with decreasing applied binder strain, which means it's not unlike what we talked about in pavement structure. If you make the strain less, it's going to increase the fatigue life. It's going to increase the cracking resistance. So decreasing applied binder strain relative to failure strain, but also increasing the fatigue exponent. The binder strain itself is primarily a function of binder modulus, so G star. Failure strain decreases dramatically with increasing modulus. And fatigue exponent for a mixture is inversely related to the binder phase angle. In other words, you get a higher fatigue exponent with a lower phase angle. So what does all that mean if we look at it maybe in, I won't say simpler terms, but if you think about breaking it down, it says as the binder becomes stiffer, as G star increases, the fatigue life or the resistance to fatigue damage decreases. As the binder becomes more brittle, that means your phase angle is decreasing. It's becoming less like a viscous fluid and more like an elastic solid. The fatigue life or the resistance to fatigue damage decreases. So we see, and this happens with aging, stiffness goes up, G star increases, phase angle goes down. So those are both rational. In both cases, we're seeing a material that's getting stiffer and fatigue life is getting worse. Phase angle is decreasing and fatigue life is getting worse. And that's what that was basically what they were trying to say. What they looked at in this study, 959 took a look at a number of binders and evaluated those. Table 3 was kind of their principal set of binders that they studied, but it wasn't all of them. So they looked at those on the far left, but then they also took a look at some older data and derived some information based on older testing that was done. And those are also shown in tables 4, 5, and 6 here. So you can get more information from those. Oops, I went ahead too quickly. So as far as some more key findings, we're talking about binder failure strain and how it's determined and what it is. What we look at under fatigue loading and a given set of conditions, you can calculate that failure strain, and it's called fatigue strain capacity, or FSC. And that's important in understanding that it determines fatigue performance, and according to the researchers, it's a good basis for a specification test. So the question is, okay, well, how does that relate? If fatigue strain capacity is what you're trying to get, how do some parameters relate to that? And what they found was that the current intermediate temperature parameter, which is G star times sine delta, is moderately correlated to binder fatigue strain capacity. They found that the Glover-Rowe parameter correlated better to fatigue strain capacity and was a good indicator of binder failure strain under a given set of conditions. These are their graphs when they mention that. So on the left, it's fatigue strain capacity. That's function of G star sine delta. And on the right is the Glover-Rowe parameter and fatigue strain capacity. And you can see the R squares, they are both pretty decent relationships. The Glover-Rowe on the right-hand side is a much stronger relationship, not as much scatter as you can see. What's on the left with G star times sine delta is not bad. And I think, you think back to what we showed earlier with the work that they did in SHARP report A388 and the relationship between mixture fatigue life and G star sine delta. And they didn't have bad relationships there either. It wasn't great, but certainly not bad. So what the researchers were finding was basically that they had better correlations with the Glover-Rowe parameter. So because of that, they recommended that Glover-Rowe parameter should replace G star times sine delta. And if you've not heard of the Glover-Rowe parameter before, it's got the same form in general as G star sine delta, but it also adds in the cosine of delta that's squared. So it's a little bit more of a complicated term, and you can see that there. But what it does in effect is it relies a little bit heavier on phase angle, which is the fatigue exponent that we talked about earlier. So if you have a lower fatigue, or if you have a lower phase angle, then the Glover-Rowe parameter is going to increase. If you have a higher phase angle, it's going to decrease. That's the way that it works. And it doesn't necessarily work exactly the same way with G star sine delta, which is why one of the reasons why they recommended to do this. They did recommend keeping it at the same frequency, so it's still run on the DSR. It's still the same frequency. It's not much challenge there. And they recommended that for 20-hour PAV that limit should be 5,000 kilopascals. Another key finding that they had was that there is significant evidence that suggests fatigue performance is related to R value, and allowable range of R value would also help to ensure good fatigue performance. So what they've found was that binders with really high R values perform poorly in thin pavements, and binders with low R values tend to perform poorly in thicker pavements. But generally speaking, Higher R values are related to more negative delta TC values. And that's been associated with increased non-load associated cracking. Positive delta TC values are correlated with lower R values. And so generally speaking, you see adequate or even good performance depending on the pavement itself. Of the two, the higher R value is more, I guess, more important in making sure that you get good performance. And that's kind of what this says here is, and I'm not going to go into, the layered elastic response, but it talks about the results, that can happen. And theoretically, there should be both high and low limits on R delta TC, but recent experience suggests that the upper limit on R is really the more important one, or the lower limit on delta TC, if you will. And they left both of those as options really in the 959 research when they talked about R, even though that's principally what they talked about. They also acknowledged that R value was very closely related to delta TC, but works in the opposite way. Higher R values, lower delta TC values. Their suggestion, based on their research, was that an allowable range for the Christensen-Anderson R value should be 1.5 to 2.5 after 20-hour PAV aging. They gave some initial recommendations after 40-hour PAV, but those have yet to be a little bit more validated. But just looking at the 20-hour PAV, this is what they found. And they found that the R value could be calculated really from the BBR data. So there's a couple different ways you can get R value. This is the equation that they recommended, mainly because you already were collecting BBR data in as far as to get this R value. It really didn't require any additional testing. It just, you took data that you had from the BBR and you plugged it into this equation. In this case, stiffness is shown there in the here as the BBR creep stiffness in megapascals at 60 seconds, and the M value at 60 seconds here. They didn't give any further guidance on that. I can tell you that one of the things that we had looked at when we were looking at this definition of R value was to get a consistent response. The best way of doing it would be to get it at the specification grade temperature. So for instance, you might run if you're testing at 64 minus 22, you're going to have to run the BBR at minus 12. If you were doing delta TC work, you might also run it at minus 18. The R value at minus 12 and minus 18 can calculate a little bit differently. So in this case, for specification purposes, we would say you would want to look at the R value at the specification grade temperature, or at minus 12. The calculation is pretty straightforward, as you can see here. Plug in the stiffness 182, the M value 0.357. You do the calculations and you get an R value of 1.91. Now, there are some assumptions there, and that has to do specifically with this value, 3,000. So this is the assumed glassy modulus in bending. So glassy modulus in shear, many of us have heard about that and have roughly assumed that it's 1 times 10 to the 9th or 1 gigapascal. This case, this is 3,000 megapascals, which would be 3 gigapascals in bending. Bending, it's going to be about 3 times modulus values of what you see in shear. So that's the assumption there, is that it's a fixed glassy modulus. That's probably not a good assumption. And there's plenty of work that's out there that suggests that the modulus is going to vary within a range, but this was what they recommended within this research, was just using an assumed value of this glassy modulus to get this R value here. They also mentioned a couple of things that were not directly related to the testing, but were more related to temperatures, and that is that there seem to be two concepts that were misunderstood or, as they said in their report, simply ignored. And that's that the specifications meant to address field performance of actual pavements and not the performance of mixtures tested in the laboratory. And we tend to evaluate things versus how they're doing in the lab as opposed to in the field. But the other part that's perhaps more important is that it should be done at an intermediate temperature that's characteristic of a particular climate and not necessarily based on binder grades. And where they were coming from with that was specifically where you're looking at binder grades that have been bumped for extreme traffic levels. So the example I use to folks, like in Kentucky, standard grade for Kentucky would be a PG 64 minus 22. That's appropriate for the climate in Kentucky. Oftentimes on the high volume roadways in Kentucky, a PG 76 minus 22 would be used. If you just followed AASHTO M through 20 straight, a 76 minus 22 would be tested at an intermediate temperature of 31 degrees C. A 64 minus 22 is tested at an intermediate temperature of 25 degrees C. So what can happen is you can end up with potentially a binder that is too stiff because you're testing it at a higher temperature and allowing it to meet that specification at a higher temperature. But you can have a binder that's too stiff relative to the climate in which it's going to perform. That's why some agencies, when they've done grade bumping, have taken it back to what the climatic grade is. I think Kentucky does that, where even though it's a 76 minus 22, they have testing done at intermediate temperature at 25 degrees C. The other approach would be simply to go with what's done in AASHTO M 332, which, because it's not based on bumping the high temperature grade, but rather on traffic designations like H, V, and E, then you don't have to worry about going to too high of a grade overall. So that's what they're suggesting. And what they suggested in this research is that rather than basing it on an average of the high and low temperature plus 4 degrees C, that it should just be based on, their recommendation was just on the low PG. And this is what the table would look like of intermediate test temperatures just based on the low PG. So whether you're a 64 minus 22, a 58 minus 22, 52 minus 22, the intermediate test temperature is the same at 25 degrees C. May not be a perfect, but they felt like it got you closer to what the intent was originally. So what do we need to know about this intermediate temperature binder parameter in M320 and M332? We know that the current parameter was based on limited field data from the 50s and 60s, specifically the Zaka-Wigmore test road. We also know that multiple researchers, and it was validated through some lab testing. We know that multiple researchers have suggested that G-star time sign delta does not seem to correlate well to fatigue performance in the field. How did the 959 research team address the objectives of relating binder properties to mixture fatigue performance? They largely relied on 16 asphalt binders with a range of expected fatigue performance that included polymer modified, straight run, GTR modified, oxidized, PPA modified, REOB, VTAE blended materials. All those were included and included with laboratory fatigue tests. They relied on other older data sets, and they conducted binder and mixture fatigue testing, or mixture testing, both flexural beam fatigue and uniaxial fatigue. And what were their recommendations coming through this work? And again, you can find this in NCHRP report 982. They recommended the Glover-Rowe parameter replace G-star time sign delta and as the intermediate temperature parameter after PAV aging. Glover-Rowe is defined as G-star times cosine squared delta divided by sine of delta. They placed a maximum limit on that, just like we have for G star times sine delta. Recommended the same value of 5,000 kilopascals at 10 radians per second and the intermediate test temperature. They also recommended adding R value as an additional fatigue parameter that they calculated from BBR data. And they added that as much for durability as anything else. And we'll talk some more about that in the next part too. But they established a range of that R value from 1.5 to 2.5. And that was to keep excessively age-hardened asphalts from being used within the specification. And then lastly, they recommended that the intermediate temperatures be based only on the low temperature grade rather than being a function of the high and low temperatures. So that one would be a bigger change, and we'll talk about that as we come into the next part of this. Really, this is the next part of the presentation that we're going to do here in a couple of weeks, and that's understanding the expected impact of those research recommendations on lab operations, as well as on the PG specifications in M320 and M332. I think that's all I have, so I appreciate your attention today and happy to address any questions you might have.
Thank you, Mike. Great presentation as usual. And then building up on the part one, we do have some questions for you here today. I'm gonna start with the first one. It's a little bit more related to the delta TC at the low temperature, and specifically when working with polymer modified asphalt binders. How is that working with the current specification proposed at the intermediate temperature? Especially that with some of the polymer modified binders, data is showing a lower or a more negative value for the delta TC. If you can please, comment on that and then relate back to the intermediate testing temperature.
Sure. So what delta TC shows us and what happens particularly at intermediate temperatures is when you're using you're using rheological parameters. So we're using phase angle and relying heavily on phase angle to tell us a little bit about how the binder is having relaxation properties. Lower phase angles mean more elastic response and less of a viscous response. So it's natural for a polymer modified material, one that's got an elastomer in it, to have a more elastic component, and thus the phase angle will be a little bit less, and the delta TC will be less as well. We've seen I've seen it's a little mixed. Some materials, yes, I do see that when you modify, it moves the binder delta TC lower for polymer modified materials, but I've also seen it where it doesn't affect it much. I think it somewhat is going to depend on the formulation and what the base grade looks like.
So along those lines also, then would the Glover row parameter be run at the original intermediate temperature, or would it be run at the recommended intermediate temperatures based on the low temperature grade?
If you follow what 959 recommended, they would have it run at the new proposed temperatures, which are based just on the low temperature grade. In a lot of cases, it's not going to affect some of the binders, but in some cases it will. And I think that's probably the most challenging of the recommendations. We played a lot with Glover row already, and with R value, and can see, how that can work within a specification. Changing the temperature could really change. I think that has to be evaluated because that could really change how our current binders respond.
On slide 28, Mike, you did explain how the bumping for the asphalt binder grade is handled for extreme traffic levels?
Hmm.
The question is when reclaimed asphalt materials is used, bumping at the high and or low temperature grades can also obviously occur depending on the amount of the RAM materials in the mix. How
Right.
should that situation be addressed?
So, I guess the way that I look at it is that most often, if as you're using higher percentages of recycled materials, you're going to need a softer grade in order to compensate, for the harder recycled materials, whatever that may be. And that means that you're going to bump down. If you're looking at it in terms of a specification, if you're looking at it in terms of what's going to happen when you've got the combined blend out on the roadway, then maybe you're going to look at those combined properties and see where those are going to end up. If you're just looking at it within a binder specification, then I don't think that you're going to necessarily need to change anything. So I'll use Kentucky as an example. Again, that's what I know. If they're using a higher amount of recycled materials, and they normally would use a 64 minus 22, maybe they bump down, if you will, to a PG 58 minus 28. They still would need to meet all the properties of 58 minus 28 at that intermediate, at the intermediate temperatures, high and low temperatures. But if they're blending it and they're looking at what's the combined blend, then maybe they want that combined blend to meet the properties as if it were going to be a 64 minus 22, for instance. So I think, the question really, I guess what they were trying to address is what we see within M332 anyway, which is that just because you're bumping the high temperature grade for traffic doesn't mean you need to adjust your intermediate temperature grade. That's what the 959 research was more or less saying.
And maybe Mike, to extend on that, do you think this will still be valuable or will be more valuable, especially when you're dealing a virgin binder that is, for instance, let's say polymer modified asphalt binder, and you're adding recycled material to it?
Yeah, I think it'll still be valuable, yes. And I think it'll still, it will still be applicable as we go into that. I think partially it was really just I guess for lack of a better word, it was just some guidance to, if you're choosing to use a stiffer binder because you're worried about rutting, that don't forget that with that stiffer binder comes stiffer properties at intermediate temperatures as well. And you need to potentially you need to make sure you're testing at the intermediate temperature that's appropriate for that climate.
And then, Mike, part of this, study, especially the 959, has there been any work to correlate the mixture fatigue with the linear amplitude sweep test results?
There was quite a bit that was done during as part of NCHRP report 459 and in the 9-10 work. That was the recommendation that came out of that was looking at something like the linear amplitude sweep test that eventually became that. We've done a little bit and of work and correlating between the two. We can see a strong correlation between the B component, if you will, from the linear amplitude sweep, which is the slope. That does relate pretty strongly to what we would see when we look at things like delta TC or R value, which is not a surprise, perhaps, but there is some relationships that have been seen, yes.
Right, very good. Another question I have, with the implementation or potential implementation of the Glover row parameters, test and measurements, what is the impact of adding this test on the workflow and the lab time?
Yeah, so we'll touch on that a little bit more in the next presentation, but um, as far as Glover Row, the recommendations that they've got here and now, which is the Glover Row and the use of R value from the BBR data. Glover Row is the same DSR test that we're running currently. It's just instead of you get output of G star and phase angle, and right now the scripts on the DSR automatically calculate G star times sine delta for you and give you that number. You can change the script pretty easily, I'm sure. I'd have to talk to the DSR manufacturers, but it would be the exact same test. It's just that instead of reporting G star times sine delta, you're reporting G star times cosine delta squared over sine delta. It's just you're using the same G star and delta, just using a different term. So from an operational standpoint, I don't think the technician would ever notice it. It's the same test. As far as R value goes, the way that they recommend it in the 959 research is they're saying get R value from your BBR data. So again, in this case, you're already getting stiffness and M value from the BBR. You're just going to take S and M and plug it into that equation and calculate an R value. And frankly, I think we had I'm going to go back here. I showed it there in the gray column to the right. I mean, eventually, if that's what people wanted to do, I think the BBR manufacturers could change the report to do that calculation, just add a column to their report. So again, from the standpoint of a technician and lab operations, those two parameters, Glover Row and R value, really do nothing. It's all data that you're already getting. It's just using it in a different way.
Good. And along those lines, has there been any work related to the variability of the Glover row parameter?
Yes. And that'll be, again, that's something that I'm going to touch on in the next part of the presentation. But I was fortunate enough to be able to get some data from, let's go here to the recommendations. So I've got that on screen. I was able to get data from AASHTO Resource from just raw data from some of their proficiency sample program. And I was able to plot G star times sine delta, the variability, and Glover row. Because you're using the same, you only have variability can happen in two areas, and that's in G star determination and in phase angle determination. So when you have a term like G star times sine delta, which you see here, you got an error in G star, you've got an error in delta, you're going to have a certain error that's going to come about in G star times sine delta. When you go to Glover row, it's an error in G star, your error in delta here, that gets squared, and an error in delta here. So because I've got more deltas, if you will, I've got more opportunities for error. And actually what you find is that the Glover row parameter has a higher variability, a little bit higher variability than what G star times sine delta does. It just has, you got more chances for the errors to propagate.
Very good. Thank you, Mike. I do not see any additional questions in here. Looks like we were able to handle all the questions that came in. And I want to just take a moment to ask everyone on the call to participate in our brief survey. We just put that in the chat box. If you can please go and give us your feedback. We still have one more webinar coming up on December 4. This is basically, as you mentioned, Mike, we're going to be focusing more on the specification changes at that point, correct?
Yes, yes.
So thank you, everyone, and wish everyone a happy Thanksgiving next week, and then we'll see you in a couple weeks.
Thank you.